Greetings, everyone. Welcome to the presentation on adapting the OCaml ecosystem for Multicore OCaml. This is Sudha, and you will probably meet Ankurant, Sadiq, Tom, and Casey in the Q&A session following this presentation. Just to give a quick overview on what this talk is going to cover, we will go over what is Multicore OCaml, the motivation for this talk, the distinction between multiprocess and multicore OCaml programs, building packages with the Multicore Compiler, global state and how that affects the thread safety of Multicore OCaml programs, semantics of Systhreads, breaking changes that were introduced in the runtime during the process of the Multicore OCaml GC development, and an example of a library that was parallelized with Multicore OCaml, that is LWT. So what is Multicore OCaml? Multicore OCaml is an extension of OCaml with support for shared memory parallelism via domains and concurrency via algebraic effects. What do we mean by parallelism and concurrency in this context? So parallelism is the ability to run computations simultaneously. When these simultaneous computations are run on multiple CPUs, we will observe speedups in the running time of programs. Concurrency, on the other hand, is the ability to partition computations so that they can be executed in overlapping fashion. So OCaml 5.0 will have support for domains-only parallelism. Concurrency primitives such as fibers and algebraic effects are expected to land in the subsequent releases of OCaml after the 5.0 release. What is the motivation for this talk? So as I already told you, OCaml 5.0 with multi-core support is just around the corner. The upstreaming process has already started, and some large patches such as the safe points have been merged to trunk. There's increasing interest amongst the library authors to port their existing libraries to Multicore OCaml. So the aim of this talk is to make people aware of changes that come with the Multicore runtime so that they are equipped to deal with Multicore compatibility for the libraries. We do hope that this talk will be useful to all users of Multicore OCaml on maintaining compatibility on various different areas that we are going to cover. So at this point, we should make the distinction between multiprocess programs and multicore programs clear. Admittedly, due to the lack of multicore support, people use Unix fork syscall to speed up the execution of their OCaml programs. To convey the status of Unix fork on Multicore OCaml, Unix fork syscall is not supported in multicore programs that have more than one domain. They do function as they are expected to be when there are no more than one domain in a multi-core program. That is, when the program is still sequential, but they are expected to fail as soon as any domain is created at any point in time. So we recommend that in multi-core OCaml programs, Unix create process can be used as a replacement for Unix fork primitive. The distinction between a multiprocess and a multi-core program in this context is that in multiprocess programs, the parent process and child process have their own copy of global data, including the heap, but that is not the case in multi-core programs where the global data is shared amongst all the domains that are present. This affects the thread safety, as we shall see in a subsequent section. Before that, how do you build your package with Multicore OCaml? So the good news is that Multicore Compiler is available in opam-repository, and all you have to do is to create a new switch, as you see the command here. There are two different variants of the Multicore Compiler available in the OPAM repository. So the first one is 412 plus domains. This has support for domains-only parallelism, and this is the branch that is close to what is expected to be OCaml 5.0 soon. There's another branch, 412 plus domains plus effects, that contains support for both parallelism and concurrency through algebraic effects. We recommend that you use 412 plus domains unless you're using algebraic effects in your programs. So we have deployed some infrastructure to keep a tab on the status of the ecosystem, one of which is opam health check. Opam health check runs builds and runs the test suite of all the packages that are available in 412 on the 412 plus domains only parallelism branch once every week. And it reports any new build failures as such. You can check out the OPAM health check on the link that is visible in this slide. So this has been helpful to us to discover any incompatibility on the existing libraries, as well as it has been helpful to discover bugs in the compiler and to fix them. So the other part of this is the OCaml Multicore CI. OCaml Multicore CI is deployed on the OCurrent pipeline. It monitors a select set of widely used OCaml packages such as Ermin, Coq, etc. They are monitored for every commit that we make to the 412 plus domains branch, so that we keep a tab on the compatibility with the ecosystem as closely as possible. We do hope that this will be useful in catching any bugs early on and fixing them. So moving on, global state and threat safety. As we know that OCaml allows mutable variables, and mutable variables are widely used in many OCaml programs for both efficiency and correctness in some places. So they are fine in sequential programs, but what happens in concurrent programs that have mutable variables is that concurrent modifications of mutable variables can lead to non-deterministic results and race conditions. We are developing fuzzing tools to detect data races, and they will be available for use soon. Do check out the parafuzz talk happening in this same workshop for more details on the fuzzing tools. So the takeaway here is that care needs to be taken to ensure that mutable variable modifications are thread safe and they do produce deterministic results. In order to ensure that, what does Multicore OCaml have to offer? Multicore OCaml offers these primitives for synchronization. So the first one is atomic values. Atomic values are similar to mutable references, except that it guarantees atomicity. Internally, it uses the compare and swap operation to ensure that all the mutable references can be converted to atomic variables in Multicore OCaml programs. We have support for synchronization primitives such as mutex, condition variables, and semaphores. They are expected to work with both domains and Systhreads. Next is the domain local storage. Domain local storage provides APIs to have particular values that are local to a domain. They are stored as key value pairs, and a value that is attached to a key is local to that particular domain, and it cannot be accessed from any other domain of that program. It is GC'd as soon as the domain is terminated. We will also have a bunch of concurrent data structures such as concurrent list, concurrent queue, concurrent hash table, etc. They will be available in the parallel programming library domain slip. The concurrent data structures can be used in Multicore OCaml programs in place of the sequential data structures that exist currently. To give an example of how atomic module can be used to ensure thread safety, as we can see, this is a simple counter that increments reference by a value n. If you see this part, we have a reference variable that is starting at 0 for the counter, and it increments the counter. But what happens when we increment, when we call the increment from multiple different domains is that we cannot reason about the order in which the operations are executed. So inevitably, this will lead to some unexpected operation happening and to unexpected results. So to counter that, all we have to do here is to make this variable atomic and increment the value atomically. This will ensure that the operations are happening deterministically, and we do get the result that is expected, which is, in this case, the value is incremented by 100 and the result will be 100 in the case where we use an atomic variable, but we cannot predict what the result would be in the case when we use a reference variable. Sorry, a mutable reference. When we talk about thread safety, we know that the standard library has a lot of data structures which allow mutable values. So natural question arises on what the status of them would be. So standard library is not going to be thread safe by default. There are some mutable interfaces present in the standard library, such as queue, stack, hash table, etc., and they are not, and they will not be thread safe by default. Why is that the case? This is the case because making them thread safe will incur overheads on sequential programs that are not necessary for sequential programs at all. So the option is given to an user where they can wrap these mutable data structures with a mutex so that they are thread safe in a multi-threaded environment. Or these data structures can be replaced with their concurrent counterpart, such as the lock-free queue or the lock-free stack. Also, the memory model of Multicore OCaml guarantees memory safety even for programs that have databases. For more details on the Multicore OCaml memory model, it is recommended that you go through Bounding Data Races in Space and Time that was published in PLDI 2018. So there are some interfaces in standard library which appear to be pure, but they do use some global state internally, such as the random module or the format module or the hash table module. So what is the status of these modules in Multicore OCaml? They are still thread safe to be used in Multicore OCaml, and they can be used safely from multiple domains. The global state present in these modules internally have been converted to thread local state so that they still operate as though they are operating sequentially at the same time that they can be called from multiple domains and used without any non-determinism. So Systhreads in Multicore OCaml. Good news is that the Systhreads implementation in Multicore OCaml is compatible with the stock OCaml's thread API. So we expect that any program using threads is still expected to be run in the same fashion in Multicore OCaml as well. There are two categories in which we have to distinguish how Systhreads are going to work, namely in sequential programs and in parallel programs. So it's quite simple in sequential programs. They are expected to behave as they behave in stock OCaml, and there is no upper bound on the number of threads that can be created at any point in time. On parallel programs, there are some changes that you need to be aware of, which is that when a systhread is created from a domain, it is attached to that same domain until the systhread is terminated. So what it means is that there's going to be no load balancing on executing the systhreads. Imagine this scenario. Let's say we have two domains, domain 1 and domain 2. Domain 1 creates 100 systhreads and domain 2 doesn't create any new thread at all. So domain 1 is going to execute all the 100 systhreads until they are done, while domain 2 is going to remain idle unless it has something else to do. So there is no load balancing on the domains. If there's a need for load balancing, that has to be done manually. Threads that are registered from the C API are always bound to domain 0 so that they don't terminate unexpectedly, as termination of domain 0 means that the program has already ended. So we are slowly venturing into defense against the dark arts. There is changes in the runtime. Good news first is that there's no changes in the C API due to the stop the word parallel minor collector. So the existing C API is expected to work as such. The development of the multicore garbage collector has led to breaking changes in code that explicitly access GC internals. This is because the multicore GC no longer needs some of the GC internals, as well as it adds a few GC internals that do not exist in the stock OCaml GC. So programs that access the GC internals directly might need to be checked against the multicore GC and modified according to the multicore GC's API. The major changes in the runtime are these. Multicore OCaml has a new lazy implementation that works in a multi-domain environment. Next thing is that naked pointers, that is out-of-heap pointers, are not supported in Multicore OCaml. There is a distinction in how GC colors are operated in Multicore OCaml and stock OCaml. Some of the runtime global variables are stored in a dedicated structure called domain state. We will look at the details of these one by one. First, lazy values. So lazy values, as we know, will be forced once it is called, lazy force is called. So in Multicore OCaml, lazy values cannot be forced concurrently from multiple domains. When that happens, it leads to an exception called lazy. So we see here that the program tries to force the same lazy value from 4 different domains. When that happens, it raises an exception called lazy. How do we tackle this? One way to do that is to use the try force operation. Try force operation checks if the lazy value is being forced by some other domain. If that is the case, it returns a none. If that is not the case, it forces the lazy value and returns the result, that is some v. In case the lazy value was already forced by some other domain, in that case too, it returns the result value, that is v. We can use this primitive to force lazy safely from multiple domains. As we see here, using try force from multiple domains gives us the result that we expected in this case. Next runtime change is naked pointers. Pointers outside heap, or also known as naked pointers, are deprecated since OCaml 4.11. They will not be supported from OCaml 5.0, and they are not supported in Multicore OCaml. To detect any naked pointers present in your package, there is an useful compiler option, enable naked pointers checker, that can be enabled with the OCaml option NNP checker package that is available in the opam-repository. Once this package is installed, whenever we run a program, it keeps checking for any out-of-heap pointers present in the program and reports it as soon as it is found. Once we find the address, a breakpoint can be set on this address in GDB or RR, and the exact location of the naked pointer can be found. Once we find that, in order to fix this naked pointers that are present in our programs, we can wrap them up with an abstract tag or a custom tag, and they are good to go. There are some alternative methods of dealing with naked pointers, such as they can be treated as native integers or they can be treated as boxed integers. The next change is the domain state. So this was introduced in OCaml 4.10, and domain state stores a bunch of global variables present in the runtime in a dedicated structure called caml state. So the variables that are present in caml state are domain local. So this includes variables such as the minor GC pointers, including the young pointers, and GC stats that are tracked with the caml state values. In stock OCaml, they are currently present in the compatibility macros. It is highly likely that the support for compatibility macros will be deprecated in OCaml 5.0. So the variables that are present in camel state needs to be called from camel state itself. And it is also useful to check whether them being domain local is going to cause any changes in the semantics in their existing usages. The next runtime change is GC colors. The historical GC colors present in OCaml are black, white, blue, and gray. Since OCaml 4.12, there's no gray color in the OCaml GC, and that has been replaced with Multicore OCaml's mark stack. The GC colors used in Multicore OCaml are marked, unmarked, and garbage. Yes, they're very simple. So we can see that the terminology is different in stock OCaml and Multicore OCaml. So this means that directly referring GC colors while creating the headers or in any other place is not going to work in Multicore OCaml programs. So in order to fix this, the recommendation is that this can be replaced with a more stable API, since the GC colors API is local to the runtime, and it is not expected to be stable. In case that it is inevitable to use the GC colors, we recommend that the multicore equivalent of the stock OCaml's GC colors can be used. So moving on to an example of parallelizing a library with Multicore OCaml, we look at the case of LWT. LWT is a monadic concurrency library that is widely used in the OCaml ecosystem for concurrency. It provides mechanism for effective IO parallelism, but there is no support for CPU parallelism till now. It has support for preemptive threads via the Systhreads module. So in order to support CPU parallelism, we do something similar to preemptive threads, and we use multicore domains to offload the CPU intensive computations to all the cores that are available to us. This is how we introduce parallelism in LWT. So the domain, LWT domain, is the interface that lets us use parallelism in LWT. This is an example of how that is done. This is implemented via the parallel programming library of Multicore OCaml domains lib. Some of our primitive experiments showed good speedups up to 20 on 24 cores, as you can see in the graph here. So that was a lot of details for one talk. Let's try to summarize what we covered till now. The takeaways from this talk are that Multicore OCaml compiler is available in the opam-repository, and you can use it right now. Global data in your program needs to be handled safely in a multi-domain program. When porting your program, your existing libraries and programs to Multicore OCaml, even from multi-process programs. The standard library is not thread safe by default. People are recommended to use synchronization primitives in order to ensure thread safety. Observationally pure interfaces such as random format and hash table remain safe to be used from multiple domains. Breaking changes introduced in the runtime might affect explicit GC accesses, lazy values, and out-of-heap pointers. We hope that this information is useful for everyone with respect to compatibility with Multicore OCaml. We do hope to get support from the community for the Multicore effort. Please do try to run your library with Multicore OCaml. If there arises any specific cases of incompatibility with Multicore, please do not hesitate to contact us via the Multicore issue tracker that is linked in the slides. You can find the slides and the abstract of this talk in the link that is given in the ICFP website. We are eager to take any questions from you. Thanks. Thank you.